Okay, so yeah, thanks. So today I want to talk about some extensions of higher order model checking to effect handlers. So first, let me explain the higher order model checking, which is extensions of the model checking to higher order programs. So in this framework, so system is described as some higher order programs yielding trees, like the higher order recursion schemes and the PCF terms. So the properties to be verified is a predicate over trees. And for example, it can be a monadic second order logical formula, modal mu calculus, perhaps something like that tree automata. So then the higher order model checking is a problem to solve whether the trees yielded by the program M satisfy the formula 5. So this is a very rich framework, and it can express various verification tasks like the safety and liveness verification, including the assertion checking and termination analysis. Okay, so let's see one examples here. And here the program M defines a recursive function f, and within the body it first executes a non-deterministic choice star. And if it returns true, then the close operation is called. Here the open, close, read are some file operation, and I suppose that file resources are maintained globally in the backend. So close is called if the non-deterministic choice returns true. Otherwise, the first read operation is executed, and then the same process are repeated. And the main program first opens the file, and then recursive function is called. So first, by executing this program, first operation open is executed. So the generated trees, root node of the generated trees is that open node. And then the next non-deterministic choice is executed. So the next node is that non-deterministic choice here. And if okay, sorry. Yeah. Okay, so if it returns true, then close is called, and otherwise read is closed, and then the recursive call goes to the recursive call. But first, again, the non-deterministic choice is called again and again. So this is our trees generated by this program. So then, for example, if the properties we want to verify is that is there a no-infinite path, so it means that this program may be non-terminating. So of course, in this case, this property doesn't hold, because if non-deterministic choice always returns false, then the program is diverges. And if we want to verify these file operations are used in correct order, so then this program satisfies these properties. Okay, and recently this higher order model checking is extended for effect handlers. And effect handlers is programming features to implement control flows like the exceptions, coroutines, and backtracking, and more. Okay, so this is one simple examples using the effect handlers. So here, the first 3 lines define the effect handlers, and actually it defines the effect operation this side here. And the program starts here in the handled expression. So first, open operation is called, and next, okay, so then the generated choice is start from the open again. And here, next. Decide operation is called, and this is handled by the effect handlers here. And so then the control goes to this close, and here decide operation close takes not only the parameter x, but also takes the continuation k here from the point the decide is called. And in this close, the continuation is called by the argument true. It means that this decide operation returns a true. And then the string A is chosen, and the write and close operations are called. So this computation tree is generated. And of course, this trees satisfy the property, so model checking will be success. But if the decide close, here I modified the program to call the continuation twice here. again k holes. Then after calling the close, control go back to the decide close. Then the second continuation call is executed. So then the continuation starts from the decide operations. So decide operation returns false here, and then B is chosen, right, and close are called again. So then the generated trace is something like this one. So then the properties, the correctness of the file operations doesn't hold for this one. Okay, so this is how we can extend the higher order model checking to address effect handlers. But the problem is that the higher order model checking problem with effect handlers is undecidable. This is because if under a higher order model checking without effect handlers is decidable. This is because the effect handlers are very expressive, and actually they can encode natural numbers. And it's well known that higher order model checking becomes undecidable if the programs can use the infinite data domain like natural number. So then the higher order model checking in the presence of the effect handlers becomes undecidable. Yeah, but then the natural question is that what's a fragment where the higher order model checking is decidable? So how we can restrict the programs or effect handlers and so on to make the model checking decidable. Okay, so our contribution is to identify some class of the higher order programs where the model checking is decidable. And in this class, there is no restriction on effect handlers and no restriction on effect invocations if the invocation is handled by the tail-resumptive effect handlers. So tail-resumptive effect handlers takes this form here, this specific form, where continuation k can be called only at the tail positions. So if we consider only these effect handlers, then there is no restriction on effect handler. But otherwise, if some effect handlers are not tail-resumptive, we need some restriction. And in this work, we restrict the interpretations of effect handlers can rely only on some statically bounded number of the non-tail-resumptive effect handlers. And okay, so this is theoretical contributions, and another contribution is on implementation. We have implemented a higher order model checker for a subset of the OOPSLA'25, and it checks input programs that belong to this class, and if so, then it model checks. Okay, so let's show me the examples, what programs are accepted in this, belong to this class, and what does not. Okay, so first, I presented two examples I presented belong to the decidable class we proposed. Because in this case, only one effect handler is used. So of course, use the effect handler. The number of the effect handlers are bounded. So no problem in this case. So the problem may happen in the program that uses a potentially unbounded number of the effect handlers. So here I define the recursive functions, and this recursive functions installs new effect handlers for each call. So here, first, these examples are called non-deterministic choice. Okay, so here are all operations, including non-deterministic choice and right are handled here. And the first non-deterministic choice is called, then it handled by here, but it is forwarded to the outside. And then the result is given, then the continuation is resumed. So it is just a forwarding the operation. Okay, and then if the non-deterministic choice returns true, then raise operation is called. And this is actually this handler only handles the raise exception, so it's something like that exception handlers. And if the choice returns false, then write operation is called, and then recursive call is executed. And in this example is belongs to the decidable fragment. So because raise is handled by the nearest handler, so the interpretation, the only one handler gives the interpretation to raise. And star and right are only forwarded, so forwarding clauses tail-resumptive, so no problem in this case. And of course, we can change the argument and return the value from the operations. Then this case also is decidable. But the problem happens if we want to manipulate or continue some computation after invoking the continuation. Okay, in this case, this example is outside of our class. So then we cannot answer for decidability question. Okay. So formalization, first we have two languages, and first EPCF is a simple language. It's similar to the PCF, but only finite data domains are available, and we also support algebraic effect here. And the other one is that extensions of EPCF with effect handlers, and we defined a class, decidable class using a type system, and which support some answer type modification, answer type polymorphism. I don't explain the detail, but these two features are very important to bound the number of the handlers and allow the unbounded number of the handlers if they are tail-resumptive. And then after defining the fragment, we define the CPS transformation from this fragment to the EPCF. And the higher order model checking in EPCF is decidable. So we show that this fragment, the higher order model checking for this fragment is decidable. Okay, so last I want to mention about the implementation work. So our implementation is integrate takes the HEPCF program without annotation. So first implementation does type inference, and then the CPS transformation to the EPCF term. And then we use backend or higher order model checking tool for the CPS transform terms. And we just tested our implementation for a small benchmark, so the verification completed in less than 0.2 second, but its benchmarks are very small, so we need to more larger scale the benchmarks to test the actual performance. Okay, so yeah, that's all for my talk. Thanks.
We have time for some questions.
I have a small question about this very slide. In this, when you say K of uppercase M, what does the M range over? Is it a value or is it an arbitrary expression? And then will it be executed there, and then the result will be?
Yeah, M is an arbitrary expression. So.
Okay, and you can't resume with a computation with a.
Yeah, right. So including the effect invocation and the effect handling, arbitrary expression is.
Because that would make it undecidable, or if I mean if you could send some computation back to where the effect was raised and then force it there.
You mean that if the M? Sorry, could you?
Or we can discuss this offline.
Okay, let's thank Taro again.